today it's our particular pleasure to invite on this program Dr. Satnam Singh. He's somebody who's done some fascinating work combining functional programming with building hardware. So it's quite interesting that he's working at Google Research now on the OAK project, which is developing technology to promote secure and private computing. So he'll talk more about that. And he's worked on projects dealing with custom hardware acceleration, compiler technology at Facebook in the past, at Microsoft and Xilinx. And he's held academic positions at the University of Glasgow and the University of Birmingham. Wow. So interesting background. At the young age, he moved to Glasgow to join his father, who was there from Punjab heartland, if you like. And in one generation, he's moved pretty far into kind of heady universes. And he's done his BSc and his PhD in computer science from the University of Glasgow. He was a lecturer for some time in the Department of Electronics there, electrical engineering, and later on in the Department of Computer Science. Now, this is quite interesting. We don't see this fluidity, this seamlessness in departments in India as we do abroad. So, but after that, he left academics to join a series of companies, starting with Xilinx, Microsoft, Google, Facebook, and then he's come back to Google. He's in the area of building systems through a model-based design approach, which is expressing them in a almost mathematical language. And from that, you derive the hardware. You can do proofs, you can do verifications, and I will leave the rest to him to describe. So over to you, Satnam.
Thank you very much for the kind invitation to talk. It's a pleasure to be Kavi's Corner. Is computing a science, or is it something? Is it engineering, or is it something else? Right? And I mean, I wish it was a science, or I wish it was an engineering subject. But I think, to a large extent, it's not. Because we can't, I look jealously at my friends who are electrical engineers or physicists, because they can have a model of a bridge. They can work out how to design and build a bridge, and then they know what its properties will be about the bridge, how much load it can take, etc. And then when they build the thing, the model correctly predicts what will happen, right? And the bridge doesn't fall down, and the right amount of traffic goes over the bridge, and the right thing happens. And that's fantastic. That's a great thing about being a scientist, that you can have models of the world, and you can compute the properties of these things that you're in the world. And I think that's broadly not true of computing science, right? Where we write lots of code, we really don't know what it does and how it behaves. So all our techniques to design it and analyze it and work with it and change it and fix it are all, I think, pretty primitive. So kind of the dream for me has always been, can I come up with some specification for what this piece of software or hardware is supposed to do? I refuse to accept that there's any difference between hardware and software. They're the same thing. They're the same thing to me. So I'd like to have a specification. What does it do? And then I'd like to have an implementation, which, and then be able to relate the two together and say, yes, this implementation conforms to specification. But even that, I think, has problems, because how do I get that implementation? Well, I just sort of think, and then out of nothing, out of inspiration, I create something from nowhere, and then I have to test that it has some link to the specification. Well, that would still be a good problem to have, but I could quite distant from that. But there wasn't a link. How did this implementation get born? So my real dream, which I've not realized yet, but I'm on a journey to try and get there in my own small ways, is I want to have a specification. That's a formal specification. That's executable, that I can run, which I then want to transform step by step by step to get an implementation. And then I don't need to prove that implementation is correct. It's correct by construction. It came from the specification, where each of these transformations is a formally verified, proved correct transformation. And each transformation is doing things like adding more information to turn a specification into implementation. I need a bit of RAM here. I need 3 multipliers in parallel. This divider is shared in space. This is a scratch pad. Here I've got some caches. So what your transformations are doing is injecting information about space and time, about performance. Because a specification is like mathematics. It exists in infinite space and infinite time. And implementation is a practical thing. It acknowledges the fact that we have to make some physical artifact, and we ourselves have limited space, finite space and finite time. So what I'll talk about today is a tiny, small step in that. A small step in that direction. So that's kind of like the overall philosophy about what we're going to talk about, and I think that's what Kavi and I and others have been similar, because it's a little bit like the Oxford view of computing science, right? Many people in the Oxford Computer Lab thought like this, wrote papers like this, and wrote books about this way of thinking, which is totally unconventional, right? It's not normal thinking, right? At my company, if you went to a product group and said, "This is how I want to think," they would call security, take your badge away, and throw you at the building, and you lose your job. So you're it's a radical way. Is kind of a very radical way to think. So let's do a bit of presentation, and then I'll do a little bit of demo, and then I'd like to leave some time just to have a discussion and answer questions and so on. So hopefully you can see the title screen there. So this is a project I work on. It's an open source project on GitHub. So on GitHub, it's under Project Oak/Oak, and everything's open source. And our project is about security and privacy, about giving people and organizations control over their data, about how data moves from one place to another, what you can do with it, and under what policy can the data move. So that's the big picture of what we do. So if you go to this site in GitHub, Project Oak-Oak, you can find out a bit more about it. And particularly, I'm going to talk about go into Coq and give you a few very small demos. I'm probably going to go very fast. It's going to be very hard to understand the details of what I do. You can go to this website, and without installing any software, you can step through a whole bunch of examples yourself, just in your browser, and you can see proofs step by step. You can see a descriptions of circuits, and then see that they're correctness proofs, and you can just navigate them step by step, going forward and backwards at your own speed, all in a web page without having to install any tools. So at the end of the talk, if you're interested and you want to go in deeper and look at some of the kind of proofs, you can go to this website and you can do that. It's a great site built by Jade on our team to let other people get a feeling for what we do. So first, let me tell you the bigger problem about what we're trying to solve, and we'll zoom in. So what do I mean by security and privacy? Well, today we can encrypt data at rest. We know how to do that. We've got all kinds of fancy crypto algorithms. And we can actually encrypt data in transit. As data moves from one place to another, it's encrypted. So, it's more secure, and it goes somewhere else, and it's encrypted there. So that's kind of mostly a solved problem. But things go bad as soon as we try and compute on the data, because our processors have unrestricted access to the data. So any policy on enforcement we had before has gone away, and that's a source of problems for us. We have to end up trusting our hardware, that there's nothing malicious and wrong inside our hardware. And even beyond hardware, the core of our operating systems also have unrestricted access to data. So this is, I think, an unsatisfactory thing to do with security and privacy in the world. And things get even worse when we look at attached accelerators, so things like GPU, crypto, machine learning. So this is one thing that's kind of, I think, wrong with the world as it is at the moment. So what we want to do is develop technology, tools, runtimes to make this situation a little bit better. So we want to use things called enclaves, or secure enclaves. So let's give me an example of what I'd like to do. So here is a camera, and it's observing three numbers, 7, 3, and 8. And what we'd like to do is have a policy that says, outside this private area, someone is allowed to know the average of the numbers in the enclave, but they're not allowed to know what the individual numbers are. And they're not even allowed to know how many numbers there are. So that's like a synthetic proxy for what we mean by security and privacy. We can then send this average over a public network, and it can go to some server, some computer in the cloud. So in green, so you can imagine this as being your virtual machine running in a Google Compute Engine or Amazon or Microsoft Azure. So we'd like to divide these things that compute into a green and a red part. The green part is a secure thing that we trust, which is designed to high-level assurance and high-level isolation. And the green is allowed to see the private information that the numbers are 7, 3, and 8, and that there are 3 numbers. And it can then do a computation like compute their average. The average is public. and that number 6 can travel to the rest of the processor. And it can be travel out, and somebody else can observe it. So this is what we mean by security and privacy. In some parts of a system, we have some information, and we want to package it up and process it such that it moves under policy, and we control who can do what with what information. And we're on our project, we're trying to build infrastructure, tooling, runtimes, etc., policies, information flow control to support private computing. And the kind of place where I fit in is in the green square, trying to design hardware to our highest level of assurance so that we can prove that it's correct or have a high degree of confidence that it's correct. Because if the green is compromised, then we don't have anything. We don't have anything of value. So it's a higher requirement to make the green part of that processor correct, informally specified, and form verified than the red part. So all our systems, when we use a computer and we log in as users, and we have protection of memory and processes, etc., and our file system, that's all built on a chain of trust, of one thing that trusts another thing, that trusts another thing, that trusts another thing. But it doesn't go on forever. At some point, it comes to the end. And you've got the final anchor that provides the trust chain. And this is typically called a root of trust. And usually it's a silicon root of trust. And often it's a single chip, which in it stores the keys to the cryptographic keys to your system that is used to bootstrap all the other chains of trust that's bootstraps your operating system and Linux and all the processes, etc., that go in it. So these chips have to be designed to very, very, very high level security. So that's my current area of interest, how to formally specify and implement a silicon root of trust, because this thing really has to be built to a very high level of assurance. And we work with a specific root of trust called OpenTitan. So this is, again, it's also on GitHub. You can go and see the complete source for this. And this is meant to be like a standard for anyone in the world to build a root of trust, which has a certain API, which can then be used to, as a heart of the security heart of lots of different systems, whether they're like processors and racks or IoT devices or cameras or whatever. So I think it's a very exciting project. I mean, Google's very involved in it, but other companies are involved in it. Other universities are involved in it as well. In Cambridge, England, there's a company called Low Risk that hosts the repo for it. So if you Google OpenTitan, you can find out quite a bit about it. In fact, this is the GitHub repo for OpenTitan if you want to find out more about that. So how do I want to do it? What I don't want to do is normal hardware design, where you sit down and you write in a hardware description language like VHDL or Verilog or System Verilog, and you write lots and lots of code and you implement it. And then you write lots of tests and you keep testing and testing and testing. And you kind of hope one day you've done enough tests and it's good enough and then you ship it. Because the problem for the approaches like that, which you might even use formal methods, you might use model checkers, you might write LTL logical properties using things called System Verilog. That's good for finding bugs, but it's no good for telling you your circuit's correct, because you never know when you found all the bugs. So those approaches are great, but they're great for bug finding. And what I'm interested in is making correct circuits, not circuits that just have fewer bugs. So I'm following a particular radical approach for this, about Amish Pala at MIT. And he's written this book called Certified Programming of Dependent Types, which is all about how to use the Coq theorem prover to write specifications for your programs, make implementations in the theorem prover, prove that your implementation meets your specification, and then automatically extract the correct program. So again, this is very radical. This is not how we write software in the world. And so Adam has proposed this approach, and it very much depends on things called dependent types, using very fancy type system to try and help make this happen, and automating proofs. So it's like a manifesto, right? It's like a particular view of how you should do things. And we're trying to test this manifesto. We're trying to test this philosophy. Does it really work? And for real. And I'm going to give some concrete examples of that. So how does it work? Specifications are just written as programs, as functional programs in the Galena language, which is the language of this theorem prover. And it uses things called dependent types, which you'll see a little bit about. But these are very fancy types where at the type level, not only can you have types which tell you the shape of something, this is an int, or this is a bool, but they can have values as well, like 5, or even an expression, or even something that looks like a program in your type, so, which is kind of a crazy thing to have. Right? our normal programming languages don't have programs at the type level, right? So we then do proofs about relationships between specs and programs, and we model circuits. This is by functions functions that take lists of values in and gives you lists of values out. So each value in the list represents the input, the value of a wire at a particular point in time. So a very simple semantic model. And then once we've proved that correct and implement it, we extract system Verilog, which is a standard hardware description language. And what we do is we focus on verifying the programs, not the compiler. But in principle, you could verify. You could verify both. So let me give you a flavor for what this kind of Oxford style of design is like. So this is an example of a sorter. It's a batches bitonic sorter, and it's a sorter you build. If you have a two sorter element, this tells you how to combine something that only sorts two things into something that sorts n things recursively. And what you see there is actually a bit of Haskell code using this Lava DSL, which is a domain-specific language for doing hardware design. And it's rooted in the work of languages like MUFP done in Oxford by Mary Shearer, and Ruby by Mary Shearer and Garrett Jones. And so this looks nothing like a normal hardware description language. It's like a recursive description with higher order arguments. But it's a very powerful description, and these descriptions have got algebraic properties, and you can do transformations and proofs in them. So I think this is a totally radically different way of doing hardware, and this is how we do hardware. We do things like this. It's the same ideas, but they're plugged into the Coq Galena language rather than doing them in Haskell, as we have done for a long time. And when you implement these things, this is what it looks like. This is what that sorter looks like in a chip. We compute not on the behavior, we compute layout, and you get this beautiful, compact, high-speed sorter on the FPGA chip. So we built this system recently called Cava, and it combines the Coq theorem prover with the Lava DSL we did in Haskell, and that's why we call it Cava, the C from Coq and the Ava from Lava. And it has a very simple semantic basis, right? We just have, what is the meaning of a gate? We just think about recurrence equations over streams, right? So we just think of lists or streams of values coming in, infinite list of values coming in, infinite list of values being produced, and we just talk about the value at the current time step in terms of previous time steps. So this means we can only do one clock at a time, but for all the circuits we care about, one clock is totally fine. So in Haskell, the way you would do this is you'd have a type class, you'd overload it, and you say, what does it mean to be an inverter? What does it mean to be an AND gate? What does it mean to be a delay? And then you create an instance for this type class. Like an inverter, it just applies the not function into every element of a list. What's an AND gate? It takes two lists, it zips them together element-wise, and then you AND each element to get a new list. That's just the AND of the two inputs. And what's a delay? Well, it's just the input list delayed by one time step. So let's put a default false value at the top. So this is a standard way to model the semantics of digital circuits in a lazy functional language like Haskell. And then if you see at the bottom of the screen, you could, in your repo in Haskell, you could just evaluate an inverter. You can give it some values, false, true, true, false, and it gives you back the computation of the value of that. And then the other thing, you can then give a different interpretation, make a circuit graph. That's what lets you make an actual implementation in FPGA. And there you would write some monad stuff, which creates a graph, captures sharing. So you do a little bit of plumbing and mechanistics to do that, and then you instantiate the class of those values. And now you can make like a NAND gate. So you hear say NAND gate, it's an AND gate with the output, it's output connected to inverter. That's Kleisler composition, or it's like dot in a functional language, but the other way around, done at the monad level. And now when you run that NAND gate with simulation, you see it simulating true, 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 false. That's what you expect. But you can also generate the circuit netlist for it as well. And then you can do sequential circuits by just having loops. And for that, there's nothing special. You just write a function called loop that just takes the output of a circuit, one of the outputs of a circuit, it bends the wire and it connects to the input, which looks a bit crazy. It looks like you've got an infinite loop. And you do have an infinite loop, but it doesn't matter. In a lazy function like Haskell, a lazy functional language like Haskell of infinite lists, as long as I only consume a finite amount of my input, this works. What's really crazy about the line at the bottom is you see the C is on the left-hand side and the right-hand side of that binding arrow. In most languages, that's a compile time error or infinite loop. In Haskell, that is an infinite loop, but you can compute a finite amount of it. And this gives you quite a beautiful and simple way of describing circuits and their semantics, and to be able to make circuit implementations. So everything we do is based on these observations about how nice it is to model circuits in functional programs, right? There seems to be a really fundamental affinity there. This is what it actually looks like in Galena, in our cocktail system. So this is no longer Haskell. This is now Galena of in the Coq theorem prover. And I mean, I won't go into details, but this, you can, like, if you know Java or C++ is like an abstract base class. It describes what are the methods that are available to you to build circuits. Or what we have are, we've got constants, we've got inverters, OR gates, lookup tables, and then also we've got delays and loops like we did before. And we combine these to make to make circuits. So, for example, how would you make an AND gate? Well, if you've got an AND gate inverter, you could just instantiate them independently, just like you would do in a normal language. Like you see the X and Y at the bottom here, or you can use a Kleisel arrow, and that's your NAND gate. So what I'll do is maybe I'll take a pause there, and I'll actually maybe demo this for real. So let me stop sharing this. I'm going to share. I'm going to show you this actually, what it actually looks like. But while I do that, feel free to ask questions. Share. So this is me sitting in the Coq theorem prover. Can you see this? Can you see this code? Is that font large enough?
The font is a bit small actually. Needs to be twice the size.
Is that?
A bit larger. Yes.
Okay. So this is this is Visual Studio Code, which is what I use for editing my Coq files, and I'm just going to show you the simplest thing things I can think of, which is an AND gate. So I'm going to just load that definition up, and so it's now it's now defined, and I can now sort of move through, and I can define what an interface for it, giving the ports names. I can make a netlist for it, and I can compute the netlist. So I compute a netlist. This is the circuit that gets generated. So at the bottom, you'll see there's a netlist, and there's a NOT gate, the inverter, and it has one wire coming in, wire 0. It has one wire coming, wire coming out, wire 1. And then you see an AND gate, and it's got an output A. But the way to start this is with the AND gate, right? It's got a wire A coming in, that's one of its inputs, and a wire B coming in, and its output is wire 0. And then this wire 0 is consumed by the NOT gate, and it produces output wire 1, and that goes to the output. So we write these descriptions like this in our DSL, and they compile to. This is the machine code. It's just a circuit graph. They compile to this graph. So that's what's going. That's what's going on here. And then we can do all kinds of we can do all kinds of tests. So that's what descriptions look like. But the other thing we could have done that before, right? We could have written this in Haskell. But what we can't do in Haskell are proofs. So let me just show you what's different here. So here is an inverter circuit. It's a simplest circuit I can think of, right? So it's an inverter, and what we're going to do is a proof that this inverter is correct, right? So here is somewhere down here. I'm going to show you a proof. So I have a lemma about my inverter, and what I'm trying to claim is that if I simulate my inverter, this is that's a circuit with some input. It's the same as in Coq. We used to take the negation function and apply it to the input. So that's what it means for my inverter to be correct. And here is my attempt to do the proof. Okay, so in the right here you should see a proof window. So there's my proof obligation on the right hand side. Does simulating an inverter mean the same as mapping negation across input? So let's do the proof together. Inverter is something we've defined. So let's replace inverter with its definition. That's what CBV does. So that's now been replaced by its definition. Now let's do a little bit of rewriting to get rid of a simulate So we've got a tactic which removes the simulate to unfold it. Now we've got something that says if you map the inverted circuit and input, that's the same as mapping the negation over the input. Well, we know something about map. We know that the left and right maps, we should be able to cancel them out, right? And we've got a theorem, we've got a lemma about that we can apply. It's called map ext. So let's just apply that. There's a lemma. They've now reduced it to just inverting A. Is that the same as negating B? Well, that's the only way we can make progress here is to unwrap in. Let's do that. That unfolds into this description in the identity monad, which says take negation in the identity monad and return it. Well, we can simplify that. We can throw that ret away. And now we've got the left and right hand side are the same. And then we could apply a reflexivity tactic, and now we're done. Now we've proved that our inverter is correct. So that's what I can't do in Haskell, right? In Haskell, I can write programs and I can run them, I can type check them, but I cannot prove properties about them. And, I might want to prove a different property, like for circuit optimization. If I see two inverters together, then that's the same as a wire. Two inverters applied to some input is the same as the input. So I can tell you that, but why would you believe me? Here's a in Cork, I can do a proof. I can take the inverter, I can replace it with definition, I can do some rewriting, get rid of the maps, some stuff to do with this. Here I won't give you all the details. Do some simplification. I know that negate can be cancelled out, and then I've done the proof, right? So this is what all my kind of work looks like in for doing circuit proofs. That's what I couldn't have done with in Haskell, and that's what lets us get back to somehow being engineers again. Let me just actually get my presentation up again, which I have now closed. 1 second. Where did I put my presentation? I should have not closed that. Close that tab. Oak Drive. I shall open it up again.
We all have that problem, Satnam.
Yeah, I'm not good at multitasking, switching between things.
These wretched tabs. I've got lots and lots of them opened up on top, and then they disappear on the right-hand side.
Yeah, now my network is being terrible. I lost my presentation. That's the problem with Google Drive, right? Yeah. I have my presentation locally on my computer, but let me just wait for it to load up. But while I wait for, while it does that, let me actually just show you one other thing then. Share tab. What I showed you this in a theorem prover, but you yourself can go to you can go to this site, and you can you see what if you see I'm navigating down this site, and you can see the same output from the theorem prover. You can check it, and you can walk through the proofs yourself just by going to this website. So you can repeat everything that I did on the web page without having to install anything. So let me just get my design. I think I've got my folders come through there. I'm going to load up my talk again. But it's being very slow. Okay, there we go. Present. Okay, I've got my talk back. To present from a tab. Okay, let's get back to business. Okay, there we go. So where do we go? Let's go just zoom through all of these again. So I think we've got to a point where actually this is what the things look like, and this is another example like how you do like an adder. You could instantiate the individual components for a half adder, then you can hierarchically use a half adder to make a full adder, and then you can do a proof. Like this is a video of doing a proof. I mean, I'll just go over this the same as roughly what you what you've seen before. And then you have these higher order combinators that combine all these things together. If you've got full adder, you can make a vertical column of these, and you've got a full adder. It's just one line. And then this is how it's implemented. So on the left-hand side, you could give this to the Xilinx tools and FPGA tools. On the left-hand side, you see what the adder looks like. Then you can zoom in, and you can see all the individual adder resources on the FPGA that get used. You see it makes an efficient adder on the actual FPGA. So we've got something that goes all the way from theory to practice, from crazy dependent types in Coq all the way to individual gates, AND gates, OR gates, and registers. It closes that semantic gap. And then we have a proof that the adder is correct, which looks like, I won't go into detail, but it looks like the proofs that I just showed you before. And then you can generate the code for it here. This is some system Verilog, and that shows you, this is the machine code that's generated effectively, which we then give to the normal design tools, which then place and route it. So what we've done is, for the Silicon Root of Trust, is that we've taken components like the PinMux and the AES crypto core, and we've totally re-implemented them using our system, formally specified them, formally verified them, and then plugged our components in, made sure that all the tests pass, and then it makes sure that it really works on the actual hardware. So this is where I'm sitting. This is the laptop that's in front of me, and that's the FPGA board that runs the Silicon Root of Trust. So what we can go all the way from Coq to System Verilog to running those things in an actual Silicon Root of Trust and making it work on this FPGA board itself. And this is what it looks like when you place and route to the Silicon Root of Trust on a particular FPGA chip. So this is a PinMux component. We were able to do this completely, re-implement it ourselves. And this is, at the top, you see the system Verilog, what the engineers originally wrote. At the bottom, what we wrote. It's the same code, basically, except we've written it in a functional style. So where they would have loops and things like that, we would have maps over vectors. And then we can program, we can download the design and run it, and it does the same thing. And what's interesting is that we've managed to produce designs that are just as efficient as what the engineers wrote. So we've got total control over resources. So our designs are formally specified, formally correct, and very, very efficient, which is, I think, an unusual thing for high-level approaches. So here's an example of some of the AS crypto core. That's a key thing we focus on, because people really care that your encryption and decryption is secure. So on the right-hand side, you see the pseudocode for the cipher from the original FIPS paper on AES security. And the left is what we write, which looks like the functional program equivalent of the right. But the thing on the left is used in our proofs, is used to make our implementation of the AES circuit. What does the AES circuit look like? Well, it looks like a functional program. It looks like something that's several blocks composed together with Kleisli arrows. So it looks like a circuit diagram, a schematic. You do something with byte substitution, then you do something with shifting rows, then you do something with mixing columns, then you mix in a round key. And that's the heart of the data path of how AES crypto works. And we're able to write it nicely like this, as well as do the nice proofs about it. And then the top level look at this. And then there's a proof that shows that the inverse cipher implements inverse. So we write a lemma like this, and then we've got a proof which does that. So that's the unusual thing what we do. Not only do we do high-level implementations, we have proofs of correctness of what we do. So that's what we've done so far for hardware. And the next phase, what we plan to do is software, where we model both the hardware and the software in these systems. And then the software gets extracted to C code or RISC-V code. The hardware gets extracted to System Verilog and to communicate. And that, I think, will be a new thing, because we don't have many examples in the world where in one system, one model, we can talk about how software is doing, what's hardware doing, how do they interact with robust register interface. Because we want to verify AES.C, the driver, as well as AES.SV, the System Verilog code. So we're trying to bring these two worlds together. So that's what we've done so far, and that's kind of the future of where we're going. So that's kind of what I want to say in terms of formal presentation. Now I'm happy to go back to the Kavi's Corner part and answer questions or have a discussion or other suggestions for what we should do.
Okay, right. Satnam, this is really interesting. But something that you said resonates very strongly. And you said the Oxford view of life and computer science. And I think that sets things apart about, speaking formally, speaking in terms of mathematical entities called specifications, and then deriving a program. But what is surprising to me is that these things that we thought were the way things should be done and were revolutionary and so evident It's been almost 30 years and they haven't penetrated industry yet. I thought that functional programming would kind of, totally rule the world in a few years, but that didn't happen. I encountered Handle C, which my advisor Ian Page came up with, which was actually a fantastic way of programming FPGAs, but it didn't light the world on fire. So before we launch into the other questions, could you kind of just give us your take on why good ideas don't actually reach out at the speed that they should?
Well, my view on this is that hardware engineers don't care about abstraction. They don't care about correctness very much. They don't care about productivity. So these great ideas that we love don't solve any problems hardware engineers think about. Hardware engineers are suspicious of abstraction. They really want to control resources. They want to control how many millimeters of silicon gets used, how many nanoseconds of delay. Do you have 3 gates here instead of 2? How long is this wire? And whenever you give a hardware engineer something that's an abstraction that takes them away from colored rectangles, or this is an AND gate or not, they're suspicious, because then they don't understand what is the link between what they've written and what gets generated, because they really care a lot about the performance, what's being generated, much more than a computer programmer cares about the performance of the machine code that's generated from the high level program that they write. So I think another thing is, I've worked in hardware companies and software companies, and here's a very important difference. When you work in a software company, like a Google, a Microsoft, like or Facebook, the main thing, your main product is software. That's the main thing you make. So you will work hard to improve, the productivity of software and software engineers, etc. And everything else is a support service, right? But you really you create software with high levels of quality that you can. If you're a hardware company, the main thing you care about are colored rectangles that you're going to fabricate, make millions and millions of copies of, and ship. And then software is this necessary evil that you have to write. It's like scripting. You have to write this necessary evil to produce these colored rectangles. You hate doing it. And then when you make your colored rectangles, you go, oh, great, I've got my colored rectangles, I can now sell them. And the software you just delete and throw away because it's like a script you use to produce it, right? You don't value it. It means nothing to you, right? It just helps you get colored rectangles. Whereas the software engineers, well, the programs have value in themselves. They are the thing. They are the main thing. And that's a big philosophical difference. Then, but another part of the question is, why have programmers not taken up functional programming? I think functional programming gives you a lot of benefits to do with maybe getting more correct code, or more transformable code, more abstractable code, but clearly it's not solved problems that people care about, right? People do write in Python and PHP and do dependency injection and all these other kind of crazy things. And I think the market for correct software and correct hardware is pretty small. There's only a small number of situations where we really care about enough to do these kind of crazy things I've just talked about. And the rest of the time, we have an economic model which says ship broken stuff and then just keep shipping patches forever to just fix all the other errors that come up, right? Because you make more money if you do that, right? You make money by shipping first and being the first person to get some market, right? So you make more money shipping a broken thing quickly than a correct thing later on. If you ship a correct thing later on, you go out of business. So I think that's just a harsh reality of the world.
But Satnam, isn't it also true that the same thing that applies to hardware people applies to software people, in the sense that they just want to get the damn thing to work? This data should be transformed into this shape, and you don't care how you get there. Basically, you just hack the code. While doing it your way requires you to think and introspect and abstract. I think abstraction requires a bit more thought. So it needs a slightly mathematical outlook. I think Paritosh might have something to say here.
No, Satnam, firstly, I'm very impressed with what you're doing. Going right down from designs at gate levels, RTL level, of course, with all the programming language features which can take design right up to the modern hardware descriptions, and giving proofs of them. This is a big stack, and that you are doing it on real examples is very impressive. I think people should realize that, while, starting examples are that of, simple gates, circuits with simple gates, but you go right down to, crypto algorithms and everything. So I'm very, very, very impressed with your effort. Talking about the acceptance of these techniques in field, I worked on the Procos project way back in 90. Okay, provably correct systems, which had more or less the same dream that you are talking about. And in 2015, we had a 25-year retrospective on that. Now, there, the sound bites were a bit different from what you are saying. Of course, there it was more like preaching to the choir. They were all believers. And so they were very easy to convince that formal methods work. Yeah. But, they were saying about, the AMD floating point processor, which is fully verified using ACL and the later day theorem provers. There is this Intel's work on, equivalence checking, which goes into their chip design. I think industries come together and made, standardized specification languages like Sugar, and I guess a lot of hardware design, tools support. So what is the take on that? Are they?
Yeah, so I think formal verification has had a success in hardware, right? Because I think people, like you said, ACL2 has been used a lot for real process design. If you look at system Verilog language, it has in it these things called system Verilog assertions. It's part of the standard language. It's lots of engineers at Google use it every day, and they don't realize it, but what they're writing are linear temporal logic expressions, and then they're running Jasper Gold from Cadence to check them using a model checker, and then there are SMT solvers under the hood and things like that. So for bug finding, the use of formal methods and some formal specification with like LTL logic, that's a success story. It's one of the biggest success stories we have in formal methods. So I think that we have come a long way for bug finding. I think the thing I was trying to make a distinction at the beginning of was correctness, right? I think it's one thing. One activity is bug finding, which is a great activity, and we must have it as a very important activity. But another activity is correctness. How do you know that this thing actually completely satisfies its specification? And that's much more a rare activity, because in most situations we can't afford correctness, and we don't need it, and we don't know how to achieve it. In certain narrow situations, we can, right? Like for crypto, it's very important that's correct. Otherwise, the entire integrity of our system is compromised. Our floating point multipliers have to be correct. Otherwise, terrible things happen, right? Wrong decisions get made. So I think, I think there has been progress. I'll come back to formal methods and high level thinking and reasoning. I think this is all very important. What the whole community does is important work, even if it has no practical application today. From an intellectual and philosophical viewpoint, I think we as human beings should understand how to specify the systems we make in the world and how they operate and how to explain them, what they do. And when you do something wrong, when your car crashes or some AI algorithm arrests the wrong person or whatever, we need to be able to explain what these things are doing and why that happened and how it got to be like that. So I really think this is this area is very important, in which it doesn't matter if industry is asking us to do it. We as computer scientists should do it, right? Anyway, because philosophically it's an important thing to do.
No, I very much appreciate what your viewpoint is. Can I ask two questions? So, in your part of agenda, doing provably correct hardware designs, right? Two things, how much of this proof business can be automated, because you are really down to bit levels and, so, I just want your experience. I know it's a hard problem, but I'm sure you have things supporting, some semi-automatic kind of proofs. Corp use a lot of tactics. That was one question. Shall I ask the second one right away and then you can take both?
Let me answer. My stack depth is quite small in my brain, so I don't do most of proofs because I'm not an expert. I do proofs of work. So Jade and Ben, whose pictures you saw, do most of the proofs. So Adam's approach at MIT is heavily based on proof automation, and that is really important because one problem with doing proofs like this is if you write some code, it takes you this much time. You do a proof, it takes you like vast amounts of time to prove.
Yeah.
And then you're exhausted right after it. And then you change one line of code, then you have to redo this giant proof. So I think one problem with these type of proofs is it makes it hard to change your code. It's hard for the proofs to keep up with this pace at which code changes. So the way that people try and tackle it is with proof automation. So by using these tactics and the theorem improver to automate them, so that when somebody changes some lines of code, hopefully the proof will still work. Some automation will still pattern match the right way and unfold things in the right way. So we try and do that. But to be honest, it's hard. It's a problem. It's one thing that doesn't work well. And we actually now are in a situation where we've got some ideas about how to make our circuits better and how to modify them. But we're very careful about what changes to make, because we know that if we change this one line, then Jade has got a week of work to do to fix the proof.
So I had seen a talk once about the time of check versus the time of use problem. So in software, this is like easily solved by hashing and everything. But there was a guy called Andrew Huang, who had given a talk on like why even if you design provably verifiable hardware, someone can always implant chips in malicious. Like he called it the evil made problem. And so the moral of the story from the talk was that it should be easy for the end user to verify whether their hardware has been tampered with, basically. So could you shed some light how your systems could be useful for that or something like that? I'll just share the link.
So what we do doesn't really help about our focus is trying to design something that's correct in the first place, right? As a design, so I focus on that because that's where all the bugs and vulnerabilities, 90% of the bugs and vulnerabilities are there, and people just not being able to design the right thing. Now, as you say, even if you design the right thing, there's a ton of other vulnerabilities, side channel attacks, tampering, etc. So we only help to the extent that if somebody makes another silicon root of trust, they can. What you can do is you can take their design and then you can subject to the same tests, and you can try and subject to the same proofs and see, did it match the spec that we wrote? And if it does, then they've correctly implemented it. If not, then as for implants, except then you have to use other techniques for that. That what we the way we are currently doesn't offer anything for that. But that's a very important class of exploits. But I think when it comes to attacks, we are our own worst enemies, because we introduce most of the bugs in the system, not malicious attackers. So that's the part of this whole spectrum of problems is very, very, very wide, and I just pick one narrow part of the spectrum to work on. That's what I do. So you make a good point, but I don't have a good answer.
Yes, indeed. Okay, thank you for your answer and the brilliant talk as well. So yeah,
thank you very much.
Thank you.
So actually, I've got another talk that I'm hosting from some other people, so I have to hop up. But thank you very much for attending my talk. You can easily find my email address. If you've got any more questions for me, please feel free to ask. Otherwise, look at our websites, play with our tutorial demo, and hopefully maybe one day I can turn up in Mumbai again and give a talk in person, which would be fabulous.
We'd like to have the liberty of sending you questions, maybe which you can answer, and when we actually air the talk, right, we'll be happy to kind of air the answers to that also, because I'm sure that questions have been growing, and the area that you've been speaking about is extremely important. And I feel this is going to be the future, especially making probably correct code happen and stuff like that, especially when more and more when more and more safety critical systems are built, and you can't afford for them to fail. I think that's when it becomes extremely important, right? So thank you very much for being with us today. It's been a pleasure, and I hope to have you back in yet another episode where you can talk about some other work that you've done. This is an attempt of ours to expose our youngsters to cutting edge stuff which they might not encounter normally. And you've certainly not, you've impressed us with what you said, and we are delighted, and thank you very much for that. So that was Dr. Satnam Singh, who is a researcher at Google Research, and he's working on the very interesting area of building provably correct systems, where through an abstract mathematical level specification, we can actually derive a correct program that actually works. And as he very early on said, that most of the problem in both software and hardware is that we build a system and we don't fully understand how it works, because you start from a specification and then you separately build an implementation, and then you try and convince yourself that the implementation actually implements the specification by doing a lot of tests. And as systems become more and more complex, testing will not tell you very much. It will tell you that the bugs that you could think of don't exist, but it can't say that this is exactly the problem that you're trying to solve in the first place. And it's not actually derived from the specification. So he's working in this very important area of building provably correct hardware circuits, hardware systems and chips. And we are very thankful to him for having spent his time, taken time out of his busy schedule, spent time with us. So thank you, Satnam. It was great having you here with us. And I'm sure that we'd like to have you back again, and we'll have very many more questions for you. So thank you for spending your time. God bless. Jai Hind.